Good morning, everybody, and welcome to lecture number 5. Today we're going to talk about additive and multiplicative notation in a group setting. Before we can do that, we're going to look at a number of examples. Some examples which lend themselves naturally to what's called an additive style of notation. Other examples that lend themselves quite naturally to a multiplicative style of notation. And we're going to adopt additive and multiplicative styles of notation and get familiar with them. But first we need the examples. So consider the set Z sub n, which is the set of integers from 0 to n minus 1. There are n elements in this set. And what this is, if you think about it, this is the set of remainders modulo n. If we divide an integer by the natural number n, then the choice of remainders spans the set of integers from 0 to n minus 1. So if we have a positive natural, we have a natural number, n greater than or equal to 2, then the set of non-zero remainders modulo n is exactly this set of numbers. And this operation, the plus sign with a circle around it, we're going to use this for addition modulo n. And for all natural numbers, Z sub n and addition modulo n forms a group. And let me bend the rules just for a second. I'm going to give a first example. It's the most trivial example that there could be. But I'm going to have Z sub 1 and addition modulo 1 as the operation. And we'll look at the group table. I guess that was too easy. This group has one element in it, 0. 0 is the identity element. If we add 0 to any element, we get that element back. 0 is also its own inverse under addition modulo 1. This is a group. It's a trivial group. Now let's look at something a little less trivial, but not much less. This is the set of integers 0 and 1 under addition modulo 2. So let's look at the group table for this. Zero is the identity. So the first row is going to be exactly the same as the row of column headers above. And the first column is going to be the same as the column of row headers to the left. And modulo 2, 1 plus 1 is 2, but that's congruent to 0 modulo 2. Here's the group table of z sub 2 under addition modulo 2. Let's look at some more examples. And the integers modulo n provide some very good examples for additive group notation, which we're going to talk about after we do a few more examples. Here, z sub 3 is the set of remainders modulo 3. So 0, 1, and 2 are the possible remainders, and they're the elements of the set z sub 3. Our binary operation is addition modulo 3. 0 is the identity, so I've taken the liberty of filling out the first row and the first column of the table. Let's fill in the other cells of the table. 1 plus 1 modulo 2, let's see, 1 plus 1 is 2, modulo 3 is 2. 1 plus 2 is 3, modulo 3 is 0. 2 plus 1 is 3 modulo 3 is equal to or congruent to 0. 2 plus 2 is 4. Modulo 3 is 1. So this is the group table for the integers modulo 3 under addition modulo 3. Well, let's consider another example. The integers modulo 4 under addition modulo 4. And the elements of z sub 4 are the remainders modulo 4. 0, 1, 2, 3. 0, 1, 2, 3. Zero is the identity, so we'll fill in the top row and the leftmost column. And now we fill in the other cells. 1 plus 1 is 2, which is 2 modulo 4. 1 plus 2 is 3, which is 3 modulo 4. 1 plus 3 is 4, which is congruent to 0 mod 4. 2 plus 1 is 3, which is congruent to 3 modulo 4. 2 plus 2 is 4, which is congruent to 0 modulo 4. 2 plus 3 is 5, which is congruent to 1 modulo 4. 3 plus 1 is 4, which is congruent to 0 modulo 4. 3 plus 2 is 5, which is congruent to 1 modulo 4. 3 plus 3 is 6, which is congruent to 2 modulo 4. And this looks like it's a group. Every element of z sub 4 appears exactly once in every row and in every column. And let's check for inverses. The inverse of an element is the number that you have to add to the element to get the identity. So let's see, the inverse of 0, well, that's 0. The inverse of 1 is 3. 1 plus 3 is 0. And of course, that works the other way around as well. 3 plus 1 is 0. So 1 and 3 are inverses of one another modulo n, or rather modulo 4. So the only element whose inverse we haven't looked for yet is 2. And we find that 2 plus 2 is the identity 0. So 2 is its own inverse. And maybe we can also make an observation about this. In just a minute. Yeah, let's get back to this example and form a conjecture. 0 is its own inverse modulo n, or modulo 4 rather. We add 1 to 3 and get the identity. So 1 and 3 are inverses modulo 4. 2 is its own inverse modulo 4. So let's see. What's the conjecture? Well, the identity 0 is its own inverse. So if k equals 0, k is its own inverse. And for all of the other elements, did you notice how things worked out? 1 and 3, for example. We said 1 plus 3 equals 4, but 4 modulo n is 0. So if k is 1, then with respect to 4, 3 is n minus 1, or 4 minus 1. Does that work with 2? Let's see. 2 plus 2 is 0, but how did we get that? 2 plus 2 is 4, which is equal to, or congruent to, 0 modulo 4. So the pattern seems to be that if k is not 0, then k inverse is the number that we have to add to k to get n, which is congruent mod 0. So what do we have to add to 1 to get 4? 4 minus 1, right? 3. What do we have to add to 2 to get 4? 4 minus 2, right? And so forth. So the inverse of k under addition modulo n is 0 if k equals 0. It's n minus k if k is anything other than 0. And now let's see if we can make that work. I think this is pretty easy to prove. If k is 0, then k plus k is equal to 0 plus 0 mod n, which is going to be 0, the identity. Okay, if k is not equal to 0, then k plus n minus k is equal to k plus n minus k mod n. But this is just n mod n. I'll tell you what, forget about this mod n stuff. We'll just write that, that's equal to n. And then we'll just say that's congruent to 0 mod n. So k plus n minus k mod n is equal to 0, the identity. Hence k and n minus k are inverses. And since an inverse is unique, we don't have to go shopping around for any other candidates. So just something to remember. In addition modulo n, or in a group where the operation is addition modulo n, the inverse of a non-zero element is n minus that element. But now there's something else that I'd like to talk about now that we've seen a little bit about addition modulo n and groups of z sub n under addition modulo n. And that's the notation, because clearly when we're using addition modulo n, it's an additive operation. So we're going to talk about how we denote additive operations. Additive notation. Suppose we have a group G and the operation, the binary operation star, and the binary operation is additive in nature. Then typically we represent A star B as A plus B. So if this is additive in nature, typically we'll represent the operation as a plus sign. And what about if we add a number to itself n times? We'll call this a repetitive sum. A plus A plus A plus A plus A plus A plus A n times. We represent this as NA. And under usual arithmetic, this means n times A. Well, what is n times A? Isn't it A added to itself n times? So if we add a number to itself n times, we denote it as NA. And I should add another remark here. Suppose we just use A once. We have a sum consisting of one term A. We can represent the element A as 1 times A, or 1A, under additive notation. Now we skipped something because this thought just came to me and I needed to address it. But the inverse of A, typically we denote that as negative A. And so if negative A is the inverse of A, we have A plus negative A, which equals 0, just the way we think it should. So typically with a group under an additive binary operation, we denote the inverse of an element A as negative A. And that kind of makes sense, especially under the operation of addition modulo n, and I'll show you why. Yeah, this additive notation, use negative A for the inverse. Well, under regular arithmetic, addition and subtraction of real numbers, for any real number x, minus x is its additive inverse, so that makes sense. But there's something else to consider too. If we're a bit skeptical, we're using additive notation. And the proposal is to use negative A to denote the inverse of A. And I say rather skeptically, oh yeah, really? But it fits perfectly, it really does. For example, in the group of real numbers under addition, we use negative A as the inverse of a real number A all the time. So it's consistent with real number arithmetic. But let's look at some other groups, like maybe the integers modulo n, where the operation is addition modulo n, additive notation. So is this idea of negative A being the inverse of A really a good one? Well, let's see. The inverse of 0 is 0. So if A is 0, negative A is negative 0, which of course is 0. So that works. But what about if A is not 0? In groups where the operation is addition modulo n, the inverse of an element A, where A is not 0, is the number n minus A. That's the way it works out. So how does this notation jive with what we know the inverse to be? Negative A any two numbers that differ by a whole number multiple of n are congruent mod n. Well, negative A and negative A plus n differ by n, a whole number multiple of n. So negative A and negative A and n plus negative A are congruent modulo n. They're exactly the same number modulo n because they differ by a whole number multiple of n. But what is n plus minus A? It's n minus A mod n. So negative A is congruent to n minus A mod n, where we've already recognized that n minus A is the inverse of A. Well, minus A and n minus A are congruent modulo n. So this minus A that we'll use to denote an inverse is congruent to what we know the inverse to be modulo n. Modulo n, they're one and the same number. So actually, negative A is not a bad notation for the inverse. In addition, modulo A, negative A, and n minus A denote the same thing. They are inverses of the element A. Here's some food for thought. For any element A in the set of remainders modulo n under the operation of addition modulo n, if we add A to itself k times, we denote this sum as Ka, or k times A. Now a question might arise as, how does this notation jive with the negative A notation for the additive inverse of A? Is this style of notation, Ka to represent the sum of K terms, or a repetitive sum of A where A is a term K times, is that compatible with the negative A notation for the additive inverse of A? Well, let's see. If they are compatible, then negative NA or let's say negative Ka should be the inverse of Ka. Does that really work? Well, let's see. Ka plus negative Ka, what is that really? This is A added to itself K times. So this is A plus A K terms. And this is negative A added to itself K times. And we can associate adjacent elements in this sum any way that we want. We can take any two adjacent terms and associate them with one another before we associate any other elements together. That's what the associative law says. So in particular, we can associate these two things, but that's just 0. And then we can associate the next pair of things, but that's 0. Dot, dot, dot. The next pair of things, but that's just equal to 0. Dot, dot, dot. The first and the last elements. Yeah, I think I'm going to squeeze this in, but that's equal to 0 also. Essentially, this is a collapsing sum, and it collapses from the center out, and we get 0. So I guess the moral of the story is, as far as inverses and notation of repetitive addition, they are compatible. So let's do a review of additive notation. Here's a brief synopsis of what we've just done. With additive notation, we have a group G and an additive operator star. And we represent A star B as A plus B. Typically, that's how we do it. And a repetitive sum, let's say that we add A to itself K times, we represent that as K times A. And where it's helpful, and in some situations it might be, we represent the element A as 1A. We represent the inverse of A is negative A. And I might add also, parenthetically, that A plus negative A is the same as A minus A. So we don't make a distinction between those things. And the repetitive sum Ka, where we add A to itself K times, we represent the inverse of Ka as negative Ka. And specific examples in Z sub n, if A is non-zero, then the inverse of A always turns out to be n minus A. So those are a few things that we picked up about additive notation. And since we're dealing with additive notation, maybe we'll go on and just talk about some more things before we mention multiplicative notation. Probably what we'd like to talk about is the order of an element and the order of a group under additive notation. I guess this bit about additive notation goes quite nicely into the concept of the order of a group and the order of an element in the group. Here we go. Given a group G and binary operator star, the order of the group denoted this way, and it looks like absolute value of G. So these are just absolute value bars. This is the order of the group, and the order of the group is the number of elements that are in the group. So what if the group is infinite? If G has infinitely many elements, then the order of the group is infinity. Easy enough. Now let's talk about the order of an element. Given a group G with binary operator star, in which the operation is additive, the order of an element of the group, let's say A, is denoted this way, O of A, O for order. So this is the order of an element A in the group, and it's defined to be the least natural number n, such that n times A is the identity. And we can look at that two different ways. They're actually equivalent. The least natural number n such that A plus A plus A plus dot 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 plus A. And this is n terms here. How many times do we have to add an element A to itself to get the identity? That's the order of an element. Now, the least natural number n, the least number of times n that we have to add an element to itself to get the identity, is exactly the same as the least natural number, such that when we multiply an element by that natural number, we get the identity. Same thing. So this and this aren't just notations for the same thing. Mathematically, they're equivalent. Now let's look at some examples. Okay, let's look at our example. The group of remainders modulo 3 under addition modulo 3. Here are the elements of the group. So, what's the order of the group Z3? It's the number of elements in the group, right? Okay. So, that would be 3. Now, what about the order of the elements? The order of 0. What's the smallest positive natural number that we can multiply 0 by and get itself, the identity? Isn't the smallest positive natural number that we can multiply 0 by and get itself, the identity, 1? And here's our reason. 1 times 0 equals 0. And here, 0 is the identity. Now, what about the element 1? The order of 1, well, let's see. 1 times 1 is 1. 2 times 1 is 2 mod 2. 3 times 1 is 3, but 3 is 0 mod 3. Okay. So 3 is the least natural number that we can multiply 1 by and get the identity. Now, what about the last element, 2? Let's see. 1 times 2 is 2. 2 times 2 is 4, but 4 is 1 mod 3, isn't it? And then 3 times 2 is 6, but 6 is 0 mod 3, okay. So the order of the element 2 is 3. Now there's an interesting thing here. The order of the group is 3. The order of the identity is 1. And that's going to be true for every single group that we ever look at. In any group, the order of the identity is 1. Now, in the other cases, the order of the other elements is the same as the order of the group. We'll remember that for future reference. We had a group whose order was 3, and the order of the non-identity elements was 3 also. I wonder if that holds for all groups. And if not, what exactly is the pattern that we're seeing here? Well, we may just have to look at more examples, that's all. Z4. That looks like a good example. Here are the elements. So the order of the group Z4 is 4. Now let's look at the order of each of the elements. The order of the identity is 1, and the reason being that 1 times the identity equals the identity. Now let's look at the order of the element 1. We have 1 times 1 is equal to 1. Well, that's not the identity. 2 times 1 is equal to 2 mod 4. That's not the identity. 3 times 1 is equal to 3 mod 4. That's not the identity. 4 times 1 is equal to 4, but that's congruent to 0 mod 4. And remember that 0 is the identity. So I think we have a winner here. The order of 1 is 4. Now let's see, the order of the element 2, 1 times 2 is 2 mod 4. 2 times 2 is 4, but that's 0 mod 4. Okay, so 2 times 2 is 0, the identity. So the order of the element 2 is 2. 2 is the least natural number that we have to multiply 2 by to get the identity. And we have one more. The order of the element 3, what is that? 1 times 3 is 3 mod 4. 2 times 3 is 6, but that's congruent to 2 mod 4. 3 times 3 is 9, but that's congruent to 1 mod 4. 4 times 3 is 12, but 4 is congruent to 12 is congruent to 0 mod 4. Okay, we have a winner here. The order of the element 3 is 4. So the order of the identity is 1. No big surprise there. Some of the other elements have an order that's the same as the order of the group. 1 has an order of 4. 3 has an order of 4. The order of the element 2 is 2. So here we have an element that doesn't have order 1, and it doesn't have the same order as the order of the group either. So maybe we need one more example for us to sort of figure out exactly what's going on here. Let's look at another example. This is a nice one. Z6, under addition modulo 6. There are 6 elements in the group, so the order of Z6 is 6. Now, what about the order of 0? Well, that's the identity, so we know it's going to be 1. The order of the element 1, let's see, 1 times 1 is equal to 1. 2 times 1 is equal to 2. 3 times 1 is equal to 3. 4 times 1 is equal to 4. 5 times 1 is equal to 5. 6 times 1 is equal to 6. Whoops. But 6 is congruent to 0 mod 6. So 6 is the smallest natural number that we can multiply 1 by. and get the identity. So the order of the element 1 is 6. Now, what about the order of the element 2? Order of 2 equals, who knows? 1 times 2 is 2 mod 6. 2 times 2 is 4 mod 6. 3 times 2 is 6 mod 6, but that's 0. 6 is congruent to 0 mod 6. So we got the identity. So the order of the element 2 is 3. 3 is the smallest natural number that we can multiply 2 by to get the identity. Well, we still have 3, 4, and 5, don't we? So let's go with 3. Order of 3. Order of 3. 1 times 3 is equal to 3. 2 times 3 is equal to 6, but 6 is congruent to 0 mod 6. Holy moly, but we have it already. 2 is the least natural number that we can multiply 3 by to get the identity. Well, that was easy. Well, let's see. 4. The order of 4 equals what? 1 times 4 is 4. 2 times 4 is 8. But 8 is congruent to what? 2 modulo 6. 3 times 4 is 12. But 12 is congruent to 0 mod 6. Okay. So 3 is the least natural number that we can multiply 4 by and get the identity. Now what about 5? The order of 5 is equal to what? 1 times 5 is 5. 2 times 5 is 10, but that's congruent to what mod 6? 10 is congruent to 4 mod 6. And then we have 3 times 5, and that's congruent to 3 mod 6. 4 times 5 is 20, but 20 is congruent to 2 mod 6. 5 times 5 is 25. That's congruent to 1 mod 6. 6 times 5 is congruent to 0. Okay, there we have it. The order of the element 5 is 6. Okay. Let's just summarize what we've done and come up with a conjecture, okay? And then we'll look at one more example of a group in additive order. Here we go. In Z3 under addition modulo 3, the order of the identity is 1. The order of all of the other elements is 3, the same as the order of the group. In Z4 under addition modulo 4, the order of the group is 4. The order of the identity is 1. And the order of 2 of the elements, 1 and 3, are 4, just like the order of the group is 4. But the order of element 2 is 2. The order of the group is 4, but the order of this element is 2. Well, before we make a guess or a conjecture, let's look at the last example. Z6 has 6 elements, and the order of the identity is 1, of course, and the order of 1 is 6. The order of 2 is 3, the order of 3 is 2, the order of 4 is 3, the order of 5 is 6. Well, what do we notice about the orders of all of the elements? They're all factors of 6, aren't they? What about the orders of the elements here? They're all factors of 4. And the order of the elements here, they're all factors of 3. So what we can say is this. In a finite group, a group with finitely many elements, the order of an element, any element, divides or is a factor of the order of the group. And maybe we can make, let's see, another conjecture. If an element X in the group G where G is finite. So if an element is in a group where G is finite, the order of the element equals the order of the group. Let's see if we can figure this out. 1 and 2 have the same order as Z3. And yep, I'm going to have to quantify this. X is not the identity. But the identity always has order 1. But let's see, in Z3, the order of the non-zero elements is always 3. In Z4, those elements that also have order 4 are 1 and 3. In Z6, the elements that also have order 6 are 1 and 5. Do we see the connection? 1 and 5, these are exactly the elements that have as their greatest common divisor with 6, 1. They're relatively prime with respect to the order of the group. And I think I need to be more specific here. The order of X equals the order of z sub n, which equals n, exactly when let's see, 5 and 1, they don't have any common divisors with 6 other than 1, right? 3 and 1, they don't have any common divisors with 4 other than 1. 1 and 2, they don't have any common divisors with 3 other than 1. So I guess this is it. The greatest common divisor of x and n is equal to 1. That is, x and n are relatively prime. And in all cases, the order of an element divides the order of the group. Now, let's take a really quick look at something a little bit different. Here's our group, the set of integers under addition. The order of the group is infinity. There are infinitely many elements here. And the order of the identity is 1 for all x in the integers such that x is not equal to 0, and x is not equal to 0 for all n in the natural numbers. So in other words, there is no least natural number n such that nx equals 0. So the order of x is equal to infinity. And that makes sense because essentially the order of an element is supposed to be the number of times that we can add the element to itself and get the identity, 0. Well, if we take a non-zero integer x and keep adding it to itself, we're never going to get the identity. So we can add x to itself infinitely many times and never, ever get 0 along the way. So in this set, the integers under addition, the order of this set is infinity, or the order of the group is infinity. The order of the identity is 1. But the order of every other element is infinity. So this is a case where we have an infinite set and the elements in it, all of them, have order infinity. Well, that will conclude this lecture. I'll have another one out very soon.